Hello, Professor. So, on my 2.4 Lab 2 post lab video reflection for Module 2, my experimental design, my safety precautions were fire extinguisher at hand, clean work area, egress routes clear, never turn my back on the fire, no one in the house during the experiment, allowed loops to cool before throwing them away, kept all windows and doors shut during the experiment so I wouldn't get a through draft or a candle blowing over and starting a fire. And I also had my SDS sheets on hand while I was doing the experiment. I identified my labware or chemicals from being contaminated by, they were in sealed containers, and the labware I washed following the directions of washing your labware with distilled water, letting dry, and so forth, before I did the chem experiment. My results were let me give you my hypothesis first. When each compound is introduced to the heat source, the electrons will start to become excited and release their energy in the form of a different wavelength, producing its own color on the spectrum. My findings: the light seen by the naked eye is visible light, and the color of the light identifies the wavelength or energy amount needed to get the electron to move up, which is absorption, up a shell, or down, which would be the emissions, the loss of the electron from one shell going downwards. The color would indicate where on the spectrum that falls, the amount of energy required to remove that electron from one shell to another. So you need red needs red, yellow needs yellow. Yellow can't move red, red can't move yellow. So my findings were with the lithium chloride, my observations were it crackled, it was violet in color, and I did notice I used time. I didn't give my dependent and independent variables. So my independent variables were compounds used, time, length of time, and fire. I used time as a variable because I did notice that I would get a reaction the longer I let some of these sit inside the fire versus just immediate reaction. My dependent variable, different color on the spectrum produced. And then I used reached excited state as a dependent variable. That would be in conjunction with my time independent variable. My controlled variables was time. I controlled the amount of time that the compound was inside the flame. So back to my observations. I noticed that the lithium chloride, actually all of these, they crackled quite a bit, almost like water. And when you throw it into a fire, it was crackling off. The lithium chloride was violet in color, and it only took a quick second for that to react, for that energy to produce a color on the spectrum. My chloride, a sodium chloride, I did notice that there was a deposit buildup in the middle of the loop, which was quite interesting, almost like a charcoal, like a coal buildup. And then all of a sudden it would break and go away once it heated up a little longer. It took about 3 seconds for that one to produce a yellow looking flame or color to it. My potassium chloride, light blue is what I saw. 4 seconds for that one to really kind of come to life and produce. Calcium chloride, reddish orange, kind of a reddish orange, but majority of it was red, I suppose. 4 seconds also to come to fruition. Electron configuration, my potassium, which is written down, so I'm not going to give you that one. My lithium was 1s2, 2s1. And how I came about that was my first shell was full, my 1s2 was full, and it brought me with my helium and hydrogen, and then brought me down to the first S1 of row 2 for lithium. My sodium, 1s2, 2s2, 2p6, and 3s1. Again, just follow it down through the shells, and sodium falls at 3s1. My calcium, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Same process was followed to get that configuration. Again, my colors were violet, yellow, blue, red. Wavelengths, violet, 400 to 435, yellow, 580 to 595, blue, 435 to 480, and red, 650 to 750. Now with the blue, like I said, I called it a light blue, so I'm going to assume that that was more on the low end of the scale of 435 or so. Red with a mix of orange in there. I'm going to guess that's on the low end of the wavelength scale of 650. Go on to do the critical thinking. Supplemental knowledge. I did not. I only used our textbook. For any outside sources, I did not seek any outside sources. I felt like our textbook would, that it afforded us enough knowledge to do what we needed to do. Critical thinking prompts. Principles of both flame test and emission spectrum. We can identify, so what are the underlying chemistry principle applications in both your flame test and an atomic emission spectra. We can identify what chemical compounds, if unknown, by introducing them to heat, by the color of the spectra that they release. It'll help identify those things. Explain the process of writing the electronic configuration for each metals and the salt compound used. How did you do it? Did you know you did it right? From the homework. That's all I can say. I am still a little fuzzy on when the D comes before the P, or the S, I'm sorry, when the D level loses an electron versus the S level. So I am still a little confused on that, but I'm working through it and I'll get there. But that's it for now. Thanks, Professor. Bye.